Imagine staring into the night sky and knowing, not just believing, but truly realizing that somewhere out there in the vast ocean of stars lies a force so powerful, so utterly massive that it could swallow not just our sun, not just our solar system, but entire galaxies with room to spare. This isn't science fiction. This is Holm 15A. It sits quietly in a distant corner of the cosmos, over 700 million light-years away, at the heart of the Abell 85 galaxy cluster. From Earth, it looks like just another distant galaxy, faint, fuzzy, unassuming. But beneath that blurred glow lies something so extraordinary it stunned even the most seasoned astrophysicists, possibly the heaviest black hole ever discovered in the observable universe. Let's pause for a second and think about the words e-black hole. For most of us, that brings up images from movies, spinning cosmic whirlpools, ripping apart spaceships in scenes of sci-fi chaos. But the truth is stranger and far more fascinating than fiction. A black hole is the final act of a collapsed star or the monstrous core of a galaxy where gravity has gone so extreme, not even light itself can escape its grasp. You could throw a flashlight into it and you'd never see its beam again. That's because black holes don't just pull things in, they warp the very fabric of space and time. Now here's where it gets truly mind-bending. Most black holes are relatively small, a few times the mass of the Sun. Some, like the one at the centre of our Milky Way, Sagittarius A, are supermassive, housing millions of solar masses. That's impressive. That's cosmic royalty. But Holm 15A? That's an emperor among emperors. Astronomers estimate its central black hole may weigh in at an inconceivable 40 billion times the mass of ours. Just let that sink in. If you tried to compare it to our solar system, you'd need over 10 trillion Earths just to match its mass. It's so huge, so utterly enormous, that it defies the known models of how black holes form and grow. It's not just an outlier, it's a full-blown cosmic anomaly. When the discovery was first announced, some scientists thought it had to be a mistake. This couldn't be real. A black hole this massive couldn't be hiding in plain sight, undetected all this time. But as more data poured in, doubts gave way to awe. How did this thing get so large? Where did it come from? And most puzzling of all, what does its existence mean for the future of astrophysics? Before we dive into the answers and ask even more questions, we need to understand the playing field. We must first explore the strange, often terrifying world of black holes and what makes discoveries like Holm 15A so revolutionary. Because when you learn the full story of Holm 15A, you won't just be amazed at the scale of the universe. You'll realize that not even science knows the limits of what might be out there in the dark. And that's not scary, that's exhilarating. So buckle in. This is the story of a sleeping giant in the cosmos, a celestial monster hiding in plain sight, a heavyweight champion of the universe. This is the story of the heaviest black hole ever discovered. The discovery didn't come with fireworks. There was no cosmic explosion, no sudden flare in the sky, just a quiet revelation, a whisper in the data collected by one of the most powerful telescopes on Earth. That whisper, however, would soon roar across the astrophysics community, forcing scientists to rethink what they thought they knew about the upper limits of black hole mass. It began, like so many discoveries in astronomy, with light, or more precisely, an unusual absence of it. In 2019, a team of astronomers was studying the central galaxy of the Abell 85 cluster, a giant elliptical galaxy known as Holm 15A, or simply Holm 15A. Situated about 700 million light-years from Earth, this galaxy had already earned a reputation among researchers due to its sheer size. It had an enormous diffuse structure with a strange, unusually faint brightness at its core. What made Holm 15A stand out wasn't just what was visible, it was what wasn't there. Most galaxies, even the older and more massive ones, get brighter toward their centers. Stars pack in tighter and tighter, creating a luminous core. But Holm 15A was different. Its central region was dimmer than expected, almost hollowed out, like something had carved out the heart of the galaxy. That something, as the astronomers soon suspected, was a supermassive black hole. But not just any black hole. Using data from the Very Large Telescope, VLT, operated by the European Southern Observatory in Chile, researchers began reconstructing the galaxy's mass distribution. They measured the motions of stars, charted the light profiles, and analysed how mass was influencing the galaxy's structure. The more they studied it, the more they realised the stars at the centre were moving far faster than they should have been. Fast movement in the core region usually means one thing: an immense gravitational pull. Something invisible and incredibly heavy had to be anchoring them, holding them in tight orbits, even though no light was coming from it. As the team plugged the numbers into their models, trying desperately to make sense of the speed, the density, and the emptiness, an astonishing figure emerged: a black hole with a mass of around 40 billion suns, 40 billion solar masses. To put that into perspective, if you were to replace the sun in our solar system with this black hole, every single planet, all the way out past Pluto, would be swallowed whole, and that would barely scratch the surface. Even by cosmic standards, the number was staggering. The largest black hole directly imaged up to that point, Matey 7, had only around 6.5 billion solar masses. The black hole in our own galaxy, Sagittarius A, is a mere 4 million. This one was different. It was in a category all by itself. And yet, this behemoth had been sitting out there in the cosmic darkness, unnoticed and undetected for decades. What's more, the sheer size of the emptier core of Holm 15 matched this possibility. According to galaxy formation theories, when two massive galaxies merge, each with its own supermassive black hole, the black holes will orbit each other for millions of years before finally colliding. During that time, their combined gravitational forces kick nearby stars away from the center, creating a light deficit core. The bigger the black hole that's formed, the bigger the hollowed-out region in the galaxy. Holm 15A's core, one of the biggest ever observed, spanning thousands of light years, everything lined up. The luminosity drop, the stellar velocities, the mathematical model. All signs pointed to something unprecedented: an ultramassive black hole, heavier than anything previously confirmed in the observable universe. Astronomers around the world didn't believe it at first. The news was met with questions, challenges, and plenty of skepticism, as it should have been. After all, extraordinary claims require extraordinary evidence, but the more the data was reviewed, the more it held up. The black hole at the centre of Holm 15A could very well be the most massive ever found. And just like that, humanity had a new contender in the ever-growing pantheon of cosmic giants. But what makes this discovery truly exciting isn't just the numbers or the surprise, it's the mystery. Because if Holm 15A hides a black hole this big, how did it come to be? Could there be other giants lurking out there, even bigger, even darker, waiting to be discovered? And most important of all, what does this tell us about the wild, unpredictable evolution of our universe? The story was only just beginning. To understand the monster hiding in Holm 15A, we have to take a step back, not just a few centuries or millennia, but billions of years, to a time before galaxies had even formed. Back when the universe was still young, chaotic, and full of swirling clouds of gas, the foundations for this cosmic giant were already being laid. Holm 15A didn't appear overnight. It wasn't born like a star, and it didn't suddenly pop into existence. It is the result of countless cosmic events unfolding over unimaginable spans of time. Picture a slow-motion avalanche in space, galaxies colliding, stars being consumed, black holes merging into larger and larger beasts, because Holm 15A isn't just a big galaxy. It's a fossil, a galactic graveyard built from the remains of dozens, maybe hundreds of smaller galaxies that collided and merged to form what we see today. Each of those galaxies likely had its own central black hole. And when those galaxies merged, so did their black holes, fusing over billions of years into the Leviathan astronomers believe now lurks within Holm 15A. Welcome to the concept of galactic cannibalism. It sounds grim, and it is, but it's also perfectly natural. In the cosmos, bigger galaxies eat smaller ones. It's how the universe organizes its structures. Small gathers into large into even larger. Over time, these galactic mergers sculpt behemoths like Holm 15A, but these aren't gentle unions. When galaxies collide, their stars don't necessarily smash into each other. Space is too vast for that, but their black holes do. And black hole mergers aren't just rare cosmic fireworks. They're the engine behind the formation of the most massive black holes in the universe. In the case of Holm 15A, scientists believe its ultramassive core is the result of multiple black hole mergers, perhaps a chain reaction across deep cosmic time. With every merging event, the central black hole would have grown larger, feeding not only on stars and gas, but on the gravitational cores of other galaxies. It's likely that Holm 15A grew within a dense, rich environment, like a galactic jungle, surrounded by other galaxies in the Abell 85 cluster. In such a setting, mergers weren't possibilities, they were inevitable. And what's left behind is something terrifyingly beautiful. A galactic colossus whose heart is governed by a black hole so massive it has warped everything around it for millions of light years. But what about the stars in the galaxy? Where did they go? That's where things get even more fascinating. You see, when two galaxies with supermassive black holes collide, those black holes begin to orbit one another before eventually merge. During this process, they sling nearby stars outward, ejecting them from the galactic center at astonishing speeds. This process forcibly clears out the core, creating what scientists call a core-scoured elliptical galaxy, and Holm 15A is one of the biggest examples of this phenomenon ever found. It's not just a galaxy with a big black hole. It's a galaxy missing part of its glowing heart. That strange, faint central brightness astronomers noticed isn't a glitch or an error. It's a fingerprint, a sign that a massive rearrangement of galactic structure happened here. Something so powerful reshaped the entire core of the galaxy and flung untold numbers of stars either into distant orbits or out of the galaxy entirely. It may sound bizarre, even unreal, but our universe is built on these extraordinary events. Mergers, collisions, and cosmic violence are how galaxies grow. In fact, it's expected that our very own Milky Way galaxy will someday merge with Andromeda, and when it does, their central black holes will circle and eventually combine, giving birth to a new, larger black hole. Perhaps one that could rival some of the biggest around. Now picture that kind of merger happening not once or twice, but over and over again across billions of years in an environment filled with massive galaxies. That's how Holm 15A was forged, in cosmic fire, through epic, slow-burning acts of destruction and rebirth. So when we look at Holm 15A today, we're not looking at a normal galaxy. We're staring into a monument built by ancient collisions, a giant standing tall in a cluster of smaller siblings, with a black hole at its center that dwarfs every other we've been able to confirm. It's a silent story of violence, growth and transformation, written in starlight and shadows. A story that took billions of years to unfold, and yet its effects can be seen in one snapshot captured by a telescope on Earth. What lies at the center of Holm 15A is not just heavy, it's historic. And the deeper we look into its structure, the more we find ourselves asking, is this the final form of a black hole's evolution, or just the beginning of something even more extreme? You can't see it, not because it's too far away, though it is over 700 million light years from Earth. Not because it's hidden behind cosmic dust or cloaked inside a nebula. No, the reason you can't see the black hole in Holm 15A is far more profound. It's completely invisible. Black holes, by their very nature, emit no light. They don't glow, they don't shine. They don't reflect cosmic rays or shimmer in the darkness. They devour light and anything else that comes too close. So how do we know one is even there? That's the beauty of modern astronomy. We don't necessarily look for the black hole, we look for what it does. Think of it like wind. You can't see the wind, but you can watch its effects. Trees bending, leaves swirling, ocean waves rising. In the same way, black holes reveal themselves not through visibility, but through gravity. And in the case of Holm 15A, all the footprints, the subtle distortions, the abnormal darkness of the core, the incredible speeds of surrounding stars, lead to one conclusion. Something enormous and invisible sits at its center, but uncovering this cosmic monster didn't happen overnight. It took patience, precise instruments, and a whole lot of science. Enter the Very Large Telescope VLT, one of the most powerful observatories on the planet. Perched high in the dry Atacama Desert in Chile, far from city lights and atmospheric distortions, the VLT is equipped with a tool called MUSE, short for Multi-Unit Spectroscopic Explorer. Let's decode that. MUSE allows scientists not just to take pictures of space, but to analyze it, breaking down the light from galaxies into its component colors, or spectra. This allows astronomers to measure how fast stars are moving, how hot they are, and how far they've been stretched by the gravitational influence of nearby masses. Think of it like taking an X-ray of a galaxy, except instead of bones, you're seeing gravity in action. When astronomers pointed Muse at Holm 15A, they saw something astonishing. Stars near the center of the galaxy were moving incredibly fast, much faster than expected, hundreds, even thousands of kilometers per second. The only explanation, a huge gravitational force pulling them inward. But this wasn't just any big object. You'd need billions of solar masses to cause those kinds of speeds and that kind of motion. And still, there was no visible mass at the center, no dense swarm of stars, no nuclear light source, just a cold, dark void. That's when the idea started to form. This wasn't just a normal supermassive black hole. This was something far more extreme. Now here's the catch. No one can actually see that black hole, and we probably never will. It doesn't radiate. What we see instead is what's missing, a central region eerily devoid of stars. A colossal void, like a scar left from ancient galactic violence. This void was the smoking gun. Using complex models that simulate star motion, light profiles, and galaxy mass distribution, researchers reconstructed the gravitational landscape of Holm 15A. They simulated what kind of black hole mass would be needed to reproduce what Muse had observed. And when the numbers came back, jaws dropped. A black hole between 34 and 40 billion times the mass of our Sun. To understand the scale, imagine this. If you were to replace our Sun with this black hole, its event horizon, the point of no return, would stretch beyond the orbit of Pluto. In fact, it could swallow the entire solar system 10 times over, and still leave room for seconds. That's what lives at the heart of Holm 15A, and yet we didn't find it by seeing it. We found it by examining the silence it leaves behind. An absence of light, a clearing of stars and motion patterns so extreme they could only be explained by an unseen beast. This method, observing the surroundings rather than the subject itself, has become one of astronomy's most powerful tools. In fact, it's how we discovered most black holes to date. Rarely do we get the opportunity to see them directly, like with METI 7's stunning image in 2019. Usually, we build a case from shadowy clues, like cosmic detectives. But there's something poetic in that, isn't there? The biggest, most powerful object in the observable universe, quiet, dark, hiding in plain sight, and yet its gravity betrays it. It shapes the movement of stars, distorts time, and carves out the very structure of the galaxy wrapped around it. Holm 15A's central void is more than a missing piece. It's a declaration, a gravitational screen that stretches across space and time. Something massive lives here. And while we may never see it with our own eyes, the evidence is written in the starlight, or more accurately, in the places where starlight fails to shine. The question now becomes, if this black hole is real, as all the signs suggest, what are its implications? Because something this heavy doesn't just raise eyebrows. It challenges everything we thought we knew about how black holes grow and how big they can really get. It's one thing to say something is big. It's another to truly comprehend how big. When astronomers calculated the mass of the black hole in Holm 15A, the number itself was already staggering, up to 40 billion times the mass of our Sun. But unless you deal with galactic physics every day, that number can feel abstract, like trying to imagine how many grains of sand are in the Sahara Desert. So let's break it down. The entire Milky Way galaxy, with its hundreds of billions of stars, is held together by a black hole only 4 million solar masses in size, Sagittarius A, located at the galactic center. That sounds massive, and it is, but by cosmic standards it's actually modest. Then we have METI 7, the first black hole ever imaged by humanity in 2019. That one. Around 6.5 billion solar masses, a true heavyweight sitting inside the giant Virgo galaxy. At the time it pushed the boundaries of our expectations. And then there's Holm 15A, somewhere between 34 to 40 billion solar masses. To call it enormous feels like an understatement. It defies comparison. If we could replace the Sun with this black hole, its event horizon, known as the Schwarzschild radius, the point beyond which nothing can escape, would stretch over 1,000 astronomical units, or 1,000 times the distance between the Earth and the Sun. That's 25 times the radius of Pluto's orbit. In more relatable terms, You could line up the entire solar system 10 times inside this black hole's boundary before reaching its edge. But this isn't just a cool space fact, it represents something huge for astronomy. Literally and metaphorically, because until Holm 15A, all known black holes, even the ultra-massive ones, fit snugly within a range. Their size usually corresponded with the galaxy they lived in. We call this the mass-core relationship, or the M-sigma relation. The bigger the host galaxy's bulge, the more massive its black hole. It's a formula that's held true in nearly every case we've studied, until now. The black hole in Holm 15 doesn't just break the rules, it shatters them. According to that model, the black hole in Holm 15A's core should weigh no more than around 10 or maybe 15 billion solar masses at the very most. Instead, it weighs in at more than double, possibly even triple that estimate. This has major implications. It suggests that either the models of galaxy black hole coevolution are incomplete, or there's an entirely different kind of black hole growth mechanism at play here. And that possibility has scientists scrambling to re-evaluate their assumptions. How could it have grown so big? Is the standard model of a gradual feeding and mergers not enough? Could there be more Holm 15s out there, hiding in the darkness of giant galaxies we've yet to probe? Some researchers have even proposed a new class, ultramassive black holes, objects with masses exceeding 10 billion solar masses. These monsters may form in extremely dense galactic environments and grow through multiple megamergers, consuming other black holes in a runaway process. Holm 15 may not be unique. It might be the first confirmed member of a secret society of cosmic titans. And here's another thought. If there are more of these behemoths scattered across the universe, how would we even recognize them? Detecting them is harder than you might think. For one, they often have quiet appetites. They may not be surrounded by accretion disks or shooting out jets that light up the sky, the way more active black holes do, like quasars or blazars. No, black holes like this may sit quietly, not devouring anything at the moment, making them nearly invisible except through the indirect dance of stars around them. And unless we look closely, and with the right tools, they'll stay hidden. In short, Holm 15 teaches us something profound. Our models aren't finished. For decades, we've relied on scaling laws and simulations to describe black hole growth. We believed black holes and their galaxies grew together, keeping pace, like two dancers locked in an eternal cosmic waltz. But what if one dancer started leading the dance all on its own, racing ahead, merging more rapidly, pulling more mass than anticipated? Holm 15 may be that rogue partner, and the implications stretch across the entire field of astrophysics. If we've underestimated how large black holes can grow, other predictions about how galaxies evolve, how stars form, how matter moves, and even how gravity itself plays out at extreme scales may need to be re-examined. But beyond the science, there's also the emotion, the human reaction. That moment when you sit back and realize, somewhere out there in the darkness, in the heart of a galaxy 700 million light-years away, exists a monster of such size and gravitational hunger that it bends space and time in ways we are only just starting to understand. And we only found it because we bothered to look deeper into emptiness, into a hole in the light. Sometimes tells you what's there, other times it tells you what's missing, and that too can change everything. Billions of years ago, long before Earth had formed, long before the sun had even begun to shine, something extraordinary was already stirring in the early universe. The foundations of what would eventually become Holm 15A's Colossus were taking shape, not in a single moment, but in a long, complex dance of matter, gravity, and time. To understand how a black hole this massive came to be, we have to turn back the cosmic clock to when the universe was still a wild place, full of collisions, chaos, and creation. In those first few billion years after the Big Bang, galaxies were not the enormous, stable structures we see today. They were smaller, messier, forming and merging constantly like cosmic building blocks. Think of them as newborn galaxies, learning how to walk, only instead of legs, they had gravity and gas. In the densest pockets of the universe, where matter was thick and temperatures were high, gravity went to work. Stars formed in rapid bursts, burned brightly and died quickly, many of them collapsing in on themselves to become stellar black holes. These small black holes, only a few times the mass of our Sun, were the seeds. But some didn't stay small for long. In extremely rare conditions, like being at the centre of a young gas-rich galaxy, these black hole seeds might have started rapidly feeding, growing hundreds or even thousands of times their original size. Others may have formed directly from collapsing clouds of gas, skipping the star stage entirely, emerging instantly at tens of thousands of solar masses. These are what scientists call direct collapse black holes, and they might be the ancestors of giants like the one in Holm 15A. Still, even with the perfect ingredients, growing a black hole to tens of billions of solar masses isn't easy. It takes time, and it takes mergers, and that's where Holm 15A's story really begins. Located in the crowded heart of the Abell 85 galaxy cluster, Holm 15A sat in the perfect place, a cosmic crossroads. In such dense environments, galaxies are constantly interacting and colliding in slow but unstoppable encounters. Every merger added more stars, more gas, more mass, and, critically, more black holes. Each time two galaxies merged, their central black holes spiraled toward one another. At first, they would dance in tight orbits, releasing powerful gravitational waves as they drew closer. Then, eventually, they'd collide, merging into a new, larger black hole at the center of the newly formed galaxy. Imagine this happening dozens, maybe hundreds of times over billions and billions of years. Each merger compounded the size of the central black hole. These weren't just increases in mass, they were multiplications, and as the black hole grew, so did its ability to influence the galaxy around it. More stars were pulled into tighter orbits, more gas was sucked inward or blown away by burst-like feedback events. Over time, Holm 15A didn't just become larger, it became different. A smooth, glowing monster of a galaxy with a hollowed core and a silent beast buried deep in its heart. But there's an additional twist. When black holes merge, they don't just add mass, they unleash gravitational waves, ripples in space-time that stretch across the universe. Today, instruments like LIGO and Virgo can detect those waves from smaller black hole mergers. But if we had more powerful detectors, big enough to feel the tremor of titanic mergers billions of light years away, we might have heard Holm 15A's black hole growing, wave by wave, pulse by pulse. So what exactly caused this black hole to get so absurdly big? It could be a combination of several things. Early beginnings. Holm 15A's black hole may have started with an unusually massive seed, perhaps a direct collapse black hole that skipped the smaller evolution stages. Major black hole mergers. Instead of a few, it may have merged with multiple supermassive black holes, each already billions of solar masses. A unique environment. As the central galaxy of a dense cluster, Holm 15A likely consumed galaxy after galaxy, each one donating mass and momentum to the growing core. Limited feedback mechanisms. Often, black holes slow their own growth by heating or ejecting nearby gas, a process called feedback. But what if Holm 15A's black hole was in an environment where feedback failed, allowing it to grow unchecked? It's like a cosmic snowball rolling down an infinite hill, each merger making it impossibly larger until it reached a size defied every prior estimate. And yet, even after all this growth, what we see today is still and quiet. It appears that Holm 15A's black hole is not actively feeding, not a brilliant quasar, not a raging jet-spewing core. Instead, it's a sleeping giant. Perhaps it already devoured nearly all the usable matter around it. Maybe it entered a state of hibernation, for now. Because that's what's truly eerie. This black hole is alive in the astrophysical sense. Given enough time, enough gas or another galaxy to snack on, it could wake up again, blazing fiercely, warping space-time and changing Holm 15A yet again. So the next time you look at a calm, seemingly unremarkable part of the sky, remember, galaxies can grow in the dark. Giants can form without fireworks, and sometimes the biggest beasts of the cosmos leave behind only silence, shadows and scars. From star birth to black hole mergers, from galactic cannibalism to quiet omnipotence, this is the likely story of Holm 15A's monster. It didn't appear by chance. It was built by time, gravity, and the universe's never-ending hunger for scale. If Holm 15A can exist, if a black hole weighing up to 40 billion times the mass of the Sun can quietly sit in the core of a galaxy, hidden in plain sight, then the most obvious, most unsettling question follows. Are there even bigger ones out there? The truth is, we don't know. But once you find an outlier, a rule breaker like Holm 15A, the door to speculation swings wide open. Everything we thought we knew about the upper limits of black hole size now feels less certain, less fixed. For every monster we uncover, the universe seems to whisper, "You haven't seen the biggest yet." In fact, some scientists are already talking about an entirely new category of black holes, beyond stellar, beyond supermassive, beyond ultramassive. Somewhere in the theoretical space above them sits a new term, stupendously massive black holes, SMBH. Yes, that's actually what they're called. More of an informal name than a hard scientific label, but it drives the point home. These are black holes estimated to be over 100 billion solar masses. Not just giants, not just monsters, gods of gravity. Objects so massive they make even Holm 15 look like a warm-up act. Are they real? Maybe. Some objects in the distant universe, particularly old, bright quasars detected when the universe was only a few billion years old, require black holes that formed and grew very fast, reaching several billion solar masses in what seems like the blink of a cosmic eye. These extreme cases are already difficult to explain with existing growth models. Now throw Holm 15A into the mix and the idea becomes unavoidable. The cosmos might be hiding black holes bigger than we dared imagine. Let's talk candidates. One black hole frequently mentioned in this context is Ton 618, a quasar so bright and distant that astronomers calculate its black hole to weigh somewhere around 66 billion solar masses, possibly even more, depending on the models used. It hasn't been directly imaged, and the math involves a lot of assumptions, but it's a name that keeps popping up when you look for the universe's true heavyweights. Another is AJ 287, a blazar that seems to be powered by a binary black hole system, one small, one massive. The larger of the two might weigh in at upwards of 18 billion solar masses, possibly more, though again the numbers are debated, and those are just the ones we've caught in the act of doing something, blasting radiation, bending light, disrupting nearby galaxies. But what about the quiet ones? The ones that, like Holm 15A, aren't active quasars, aren't emitting X-ray signals, aren't giving us any flashy alerts. What if the biggest black holes are the most silent? They could be lurking in the centres of hypermassive elliptical galaxies in distant clusters. Galaxies we've catalogued but not studied in detail. Some of them are assumed to contain black holes under the standard mass-core relationship. But if Holm 15A taught us anything, it's this: the relationship might break at the top end. There could be undiscovered SMBH right now, hiding inside faint galaxy cores, waiting for our technology or our curiosity to catch up. So why haven't we found more of them yet? Simple. They're hard to detect. Most black hole discoveries rely on activity, on the accretion of gas, on the emission of detectable radiation like X-rays or UV light. But a quiet black hole, one that isn't feeding, doesn't give off these signals. It just sits there, warping gravity silently. 15A was found the hard way. By analysing light profiles, measuring star velocities, and running complex simulations. Doing that for every galaxy out there in the observable universe, it's a monumental task, but one that we've only just begun. And then there's the ultimate mystery. Could black holes be hiding well beyond what we can see at all? The observable universe is limited. It has an edge, not a wall, but a horizon we can't see past, limited by the age of the universe and the speed of light. Anything beyond that? Any potential black holes sitting in unobserved cosmic real estate? We simply don't know. And perhaps we never will. But even within our observable universe, the numbers are staggering. There are approximately 2 trillion galaxies, each potentially harbouring a central black hole. If only 1 in a million of those galaxies has a black hole like Holm 15A or larger, that still means thousands of mega-gigantic black holes are waiting to be discovered. And if that's true, we're nowhere near understanding the upper end of what black holes can become. More importantly, what Holm 15A shows us is that sometimes we don't need a spectacular light show to find the extraordinary. Sometimes we need to look for the voids. The quiet areas, the dimmed cores, the places where stars are missing and space bends more than it should. Because that's where cosmic monsters dwell. And maybe, just maybe, lurking deep within a galaxy far beyond what we've yet explored, some unknowable, stupendously massive entity waits in absolute stillness, so gravitationally dominant it shapes not just a galaxy, but a cluster, even a region of the cosmic web itself. Holm 15A may not be the limit. It might just be the beginning. Until the discovery of Holm 15A's central black hole, astronomers thought they had a pretty good handle on how black holes and galaxies grow together. Models of cosmic evolution told us that galaxies and their central black holes were like cosmic dance partners, growing hand in hand through a balanced exchange of gas, mergers, and star formation. The more massive the galaxy's center, the larger its black hole would be, predictably, mathematically, beautifully neat. But then along came Holm 15A, smashing that tidy logic like a rogue wave hitting a sandcastle. Because this black hole isn't just big, it's too big. Far larger than current galactic size to black hole mass ratios would allow. That discrepancy has sparked a quiet revolution in the field of cosmology. Suddenly, long-held assumptions about the scaling relationships between galaxies and their central black holes are under serious question. That throws a wrench into more than just theoretical models. It impacts our understanding of how the universe built itself. At the heart of this puzzle is the so-called M-sigma relation, a trusted framework that links the mass of a galaxy's central bulge with the mass of its central black hole. For decades, this relationship was considered a cornerstone of galaxy evolution. Simulations of large-scale structure formation, the kind used to model how the universe evolved from the Big Bang to today, relied on it. Holm 15 challenges all of that. Its black hole mass is so disproportionate to the structure of the galaxy around it that scientists are now asking, have we misunderstood how galaxies grow these monsters? Have we perhaps been focusing on the wrong link in the chain? Because if black holes can grow faster than the galaxies around them, then perhaps it's the opposite of what we thought. Black holes aren't just passengers riding the wave of galactic evolution. Maybe they're the drivers. Let that idea ripple for a moment. What if black holes are shaping galaxies, rather than galaxies shaping black holes? That's not just scientific semantics. That's a fundamental shift in our view of cosmic evolution. Black holes exert immense gravitational influence, yes, but they also pour energy back into their environments in the form of radiation, winds, and jets. This feedback can regulate star formation, blow away gas clouds, and alter the path of galactic evolution in dramatic ways. In the current standard model, this feedback mechanism is what keeps galaxies from growing too large too quickly. It's a delicate balance. But Holm 15A suggests that sometimes that balance fails, or never existed in the first place. Could we be looking at a rare case where the black hole kept growing and growing unchecked by feedback, perhaps due to a particularly merger-heavy history or an unusual supply of fuel, or is it not rare at all? Could there be more galaxies like Holm 15A, black holes disproportionately massive for the galaxies they inhabit, just hidden beneath the limits of our instruments? Either way, the implications are fascinating and a little unnerving. Because if the M-sigma relation is not universal, as Holm 15A seems to suggest, then calculations tied to it, including everything from galaxy formation rates to black hole census statistics, need to be reworked. It doesn't stop there. If galaxies like Holm 15A are more common than we realize, it might explain a long-standing mystery in cosmology. Why do some massive galaxies have dead cores with little star formation? Perhaps an ultra-heavy black hole at the center is the culprit, not only disrupting gas inflows, but reshaping the gravitational landscape so drastically that star-birthing clouds can't even survive. And then there's the dark matter problem, another big piece of cosmic theory. If black holes like the one in Holm 15A are gravitationally dominant far beyond their immediate vicinity, could we have been misinterpreting dark matter distributions in galaxy centers? Could observations attributed to mysterious unseen matter partly be the influence of supermassive black holes we didn't know were there? Even the behavior of gravity at extreme scales may need a fresh look. Black holes are laboratories for general relativity, pushing spacetime to its breaking point. A 40 billion solar mass black hole offers one of the most intense places in the observable universe to test our theories. Could Holm 15 help scientists unlock clues to combining relativity and quantum mechanics into a unified theory of everything? Maybe, maybe not. But the possibility is there. The bottom line is this: Holm 15A is more than just a record-setting black hole. It is a challenge to the framework humanity has built for understanding how the cosmos keeps itself in balance. It tells us we don't fully understand the rules of galactic evolution. It reminds us the universe is not obliged to follow our equations. Like an ancient monument buried in the dark, unearthed by accident, the black hole in Holm 15A rewrites the map of what we thought was possible. It forces astrophysicists to ask daring questions. How did this form? Is nature breaking its own laws, or did we never understand them in the first place? It isn't a glitch. It's a message hidden in starlight and silence that the cosmos still holds secrets we've only begun to unravel. If Holm 15A is a mystery written in gravity, then the future of solving it lies in the hands of next-generation science and technology. Tools that can see deeper, feel subtler, and decode the silent language of the cosmos with greater precision than ever before. Because right now, even our best telescopes are pushing their limits to study giants like Holm 15A. We know it's there. We know it's massive. But to truly understand the nature of ultramassive black holes, to confirm their sizes, uncover their origins, and track their cosmic impact, we'll need something more. And fortunately, that more is already on its way. The coming decades in astronomy are poised to be revolutionary. New instruments, ground-based and space-based alike, will soon allow us to peer deeper into galactic cores, measure star velocities with greater accuracy, and detect the faintest gravitational whispers traveling across the universe. At the heart of this future vision is the extremely large telescope, ELT, currently under construction in Chile. Once complete, the ELT will be the most advanced optical and infrared telescope in the world, boasting a 39-meter mirror, almost 4 times the size of the very large telescope that helped us uncover the black hole in Holm 15A. Its resolving power will allow us to see fine details in distant galaxies, including the motion of stars near their centers, which is critical for measuring black hole masses. With its instruments, ELT could confirm or refute the mass of Holm 15A's black hole, tightening the error margins and giving scientists the data they need to see whether this really is the heaviest confirmed black hole or just the first in a hidden population. Then there's James Webb, already up in space and peering farther back in time than any telescope before it. While JWST excels at spotting the early universe, how the first galaxies and black holes formed, it may not directly weigh monsters like Holm 15A, but it will help by revealing the growing pains of other black holes at high redshifts. With it, we might finally understand how black holes are born massive, or how they grow so quickly in the early universe. But black holes aren't just visible in light, they speak in gravitational waves too. Today's gravitational wave detectors, such as LIGO and Virgo, are sensitive to stellar mass black hole mergers, dozens of solar masses at most, but mergers involving billion solar mass black holes. Those generate signals too low in frequency to be picked up by current instruments. That's where the future mission LISA comes in. The Laser Interferometer Space Antenna, or LISA, is a space-based gravitational wave observatory scheduled for launch in the 2030s. Unlike Earth-based detectors, LISA will be able to detect ultra-low-frequency gravitational waves, the exact kind produced by the merging of supermassive black holes. If 2 Holm 15A-sized black holes ever collided, LISA could hear that event ringing across the cosmos like a bell. And here's the ultimate idea. What if we could predict these anomalies before we find them? Enter artificial intelligence and machine learning, rapidly becoming essential tools in astronomy. These systems are capable of scanning vast datasets from telescope surveys, far more than a human could pass in a lifetime, and flagging anomalies, subtle patterns, and unusual outliers. With AI, we could uncover faint candidates for ultramassive black holes in existing galactic catalogues by spotting the same kinds of stellar motion patterns or core-like deficits we saw in Holm 15A, before dedicating telescope time for follow-up observations. Imagine training an AI to look for potential home-class black holes, running simulations across millions of galaxies, and letting it lead us to the next great discovery. Beyond that, our own journey as a species will shape this exploration. As space agencies and private companies begin thinking seriously about deep space telescopes, lunar observatories, and even large telescopes positioned at Earth-Sun Lagrange points, our capacity to observe black holes from more stable, unpolluted vantage points will increase dramatically. All of this points to a future where the invisible becomes observable. A future where we not only confirm the existence of ultramassive black holes, but chart their influence across galaxy clusters and beyond. Where we understand how their gravity sculpts matter, regulates star formation, and maybe even triggers or halts galactic evolution. We might even reach the point where black holes are used as standard candles for measuring cosmic distances, or where incredibly massive gravitational behemoths like Holm 15 help test the limits of Einstein's theory of general relativity, which may one day crack under the weight of this much gravity. Most thrilling of all, every one of these technologies, missions and tools will bring us closer to answering not just where we came from, but what shaped the universe into the structure we see today. And perhaps beyond that, how the universe will end. Because black holes like the one in Holm 15A aren't just interesting oddities, they are power brokers in the universe. They can call the shots in galaxy clusters, influence the trajectory of matter for millions of light years, and hold clues about the final fate of all mass and energy. What happens when all the stars burn out? When galaxies have merged, collapsed, and faded? In the end, will only the biggest black holes remain, silent kings of a darkened universe? The future of exploration, powered by technologies still in development, may one day give us the answers. Until then, Holm 15 stands as both a challenge and a promise. We've only just begun to uncover the true size of our universe's monsters, and we're finally building the tools to face them. It waits in silence. At the very heart of a galaxy 700 million light-years away, wrapped in layers of ancient stars and scattered light, something impossible lies dormant. Invisible, immovable, almost unimaginable. The black hole at the center of Holm 15 doesn't rage like a quasar or blaze across the cosmos with radiation. It sits still, a quiet king surrounded by galaxies that have come and gone, a monument to cosmic time. And even though it doesn't emit a single beam of light, its presence is undeniable. It is pure gravity, raw power, a tear in the very fabric of space-time itself, and most haunting of all, it may be just one among many. As we've travelled through this story, from its understated discovery, through its unfathomable size, to the growing questions it raises about our place in the universe, one idea rings louder than the rest. We don't know as much as we thought we did. For centuries, we've chased light through the darkness, using it to map stars, galaxies, and cosmic history. But black holes remind us that in some places, light simply doesn't go or can't escape. And yet, even in their complete invisibility, black holes like Holm 15 shape everything around them, like ghosts in the gravitational field. What makes Holm 15 a truly awe-inspiring isn't just that it's massive or ancient, or the biggest ever found. It's what it implies, that the universe is still capable of surprise. For all our knowledge, decades of astronomy, millions of observations, equations, papers, and simulations, there are still giants we didn't expect. Shadows hiding quiet worlds of influence, objects that challenge the boundaries of theory. That force scientists to stop, scratch their heads, and ask the best question any scientist, or any curious human, can ask. How? How did this black hole grow so enormous? How many more like it are out there? How can something this heavy, this powerful, exist quietly for so long? How will discoveries like this change the way we see the universe? And perhaps most thrilling of all, what else is hiding in the dark? There's no satisfying end to this story. Not yet. Because Holm 15A is not a final chapter. It's a beginning, a call to look deeper. To listen to the quiet parts of the universe, not just the noisy ones. It challenges us to accept that the biggest forces in the cosmos don't always announce themselves. Sometimes they sit in silence, motionless, massive beyond measure. Until a few photons, a few fast stars, a whisper of light staring back through a telescope hint that something is out there. And for all our advanced physics, deep space missions, and groundbreaking research, there's something deeply human about all of this, because we are, at our core, explorers. We look into the night sky not just to measure distances, but to find meaning, to understand where we came from, why we're here, and where all of this is going. And in doing that, we occasionally stumble upon things that feel almost eternal. Black holes like the one in Holm 15A are not just astronomical objects, they are time capsules. They carry the history of galaxies long devoured. They are shaped by the forces that built the first stars. They are older than our planet. They may far in the future outlive every galaxy, every star, every atom. One day the cosmos may go dark, the last stars will die, the last bits of heat will fade, and all that will remain are the black holes, silent, cold, waiting. And among them, perhaps still sitting immobile in the core of a long-forgotten galaxy, will be this giant, this monument to the ancient universe, Holm 15A, not because it wants to last forever, not because it hungers or dreams or watches, but because it simply is, solid gravity, infinite weight. A presence that will outlast empires of light. So wherever you are, and no matter how small you might feel under the vastness of the night sky, remember this. You were born in a universe that created this, a universe that writes mysteries in galaxies, that builds monsters in silence. A universe that still, after everything we know, holds stories untold, waiting to be found. Stay curious, ask big questions, keep looking toward the stars, because the greatest truths are often hiding, not in what shines the brightest, but in what refuses to shine at all.